Hello and welcome to session 5 of Unit 3. This session will introduce you to the belt of stability in nuclear chemistry. By the end of this session, you should understand the belt of stability. Let us look at belt of stability. Belt of stability can be defined as an area in a plot of the number of neutrons as a function of number of protons within which the nuclei are found to be stable. So with the plot that we have here, it indicates the band of stability where neutrons are plotted against protons. Now to interpret this, you consider a typical atom, let's say calcium, with proton number of 20. So you trace the proton number to meet the curve, and you trace the neutron number to also meet the curve. So where these two intersects, all the isotope formed at that point is said to be stable because it has proton to neutron ratio of 1:1. All nuclei or isotopes of calcium that are found around the region, especially in the color blue, are said to be unstable because their proton to neutron ratios will be more than 1:1. And an illustration is here. We have the cadmium against the cadmium where the proton number to neutron number is 1.29:1. So all elements or all nuclei below the belt of stability can undergo adjustment to become stable by emission of a particle, and all the elements above the belt of stability could also undergo emission to become stable. In the following up slides, we shall be looking at what transformations occur when the nuclei is below the belt of stability and how does it become stable. All nuclei with atomic number greater than 83 or 83 and above are unstable, and so they are spontaneous. So you can realize that the red color, which indicates the stability, ends somewhere here on the plot. That is after 80, probably 84, 83, 83, 84. It is no more showing because the nuclei are stable from 83 onward. Let us look at particles that are emitted when a nuclei found itself above the belt of stability. Above the belt of stability, the nuclei has more neutrons than protons. And so to solve this problem, the nuclei undergo beta radiation. When it undergoes beta radiation, what simply happens is that a neutron is converted to a proton, thereby reducing the amount or the number of neutrons present. In this case, the ratio of neutron to proton will be reduced and the nuclei will be moving toward the belt of stability. Example is illustrated here where neutron is converted to a proton by the emission of a beta particle. Also, these examples here are radioactive decays where beta particles are emitted to stabilize the nuclei. In this slide, we shall be looking at particles that are emitted when a nuclei finds itself below the belt of stability. Whenever a nuclei is below the belt of stability, it means that the number of neutrons are less than number of protons. There will always be the need to increase the ratio of neutron to proton, and this is done by the nuclei try to move up the belt of stability. In doing this, there are two possible types of nuclear reactions that the nuclei undergo in order to move up the belt of stability. One of them is by positron emission. In positron emission, a proton is converted to a neutron, and this is what results in the emission of the positron. An example is illustrated here where a proton is converted to a neutron and a positron is emitted. So here the second example is we have potassium with atomic number of 19, which is converted to an argon with atomic number of 18. One of the protons has been converted to a neutron in the argon and a positron is emitted. Another form of nuclear reaction that nuclei undergo in order to climb up the stability belt is by electron capture. In this, the nucleus captures an electron and the electron captured combines with a proton in the nucleus to form a neutron. When this neutron is formed, as a result, reduces the atomic number by 1 and increases the neutron number by 1, while the mass number remains the same. An example is argon with atomic number of 18 can capture an electron which will combine with one of its protons to form a neutron, and so the resulting nuclei that is formed, which is chlorine, will have a reduced atomic number, and that will be 17. It is also very important to note that some of the nuclei, especially the heavy ones, will tend to increase their neutron to proton ratio by undergoing alpha emission. So when they undergo the alpha emission, it will reduce their mass number by 4 and their atomic number by 2. In this case, the proton to neutron ratio has been stabilized. Elements that have their atomic number greater than 83 are said to be radioactive, and so they undergo nuclear reactions by emitting alpha particles. Example is radium, which undergo a nuclear reaction to produce a radium by the emission of alpha particle. Also, Pu, which is polonium, also undergo nuclear reaction to give the lead, Pb, with the emission of an alpha particle. Let us also look at gamma ray emissions. Gamma rays are often emitted along with other types of subatomic particles. The gamma rays are high energy radiations which are emitted when an unstable nucleus undergoes a rearrangement of its constituent particles to give a more stable or lower energy nucleus. It is very important to note that pure gamma emitters are rare, so only few elements can purely emit gamma rays, but rather the gamma rays are radiations that accompany either alpha or beta radiations. And so we can say that radioactivity is basically a phenomenon in which electromagnetic radiations or subatomic particles are emitted by nuclear reactions so as to achieve or enter the stability belt. So example of a reaction that leads to the emission of gamma ray is illustrated here. Here, technetium is converted to technetium with the emission of gamma ray. I have placed on this slide some questions for you to try. So do well to try your hands on these questions to test how best you follow this session.